So we're going to continue now looking at optimization, finding extreme values, meaning max and min, for multivariable functions. So previously we looked at finding local extrema, and now we continue with a new type of optimization problem, finding global extrema on a boundary, also called a constraint. And the technique that we're going to use for this is something called Lagrange multipliers. So let's take a look at this, what this scenario means and where the technique comes from. Okay. So what sorts of problem are we talking about? So it's something typical where you might want to optimize something, for example, profit, maximizing profit, but you have some kind of constraint, for example, limited costs. So in single variable calculus, this optimization problem might start with a function f of xy, and that's the thing you want to optimize. And then you're given a constraint, which would look like g of xy equals k. So again, this sort of problem might look familiar. So this can be completed by solving for one variable in the constraint equation, using that to make a substitution in the function you want to optimize. So you eliminate a variable, and then you've got a function of one variable. Now you take the derivative, set equal to 0. So that is an old and familiar technique. Now it turns out that this problem, this exact problem, can also be solved using Lagrange multiplier technique. So where does this technique come from? So geometrically, we're going to look at the contour map of a function to be optimized. So now on the graph, you'll see contour lines for the function we're trying to optimize, f. Got a couple marked there. And then we also see the constraint curve. So that curve is the function where another function is the curve where another function g equals some particular value. So let's look for the point where along that curve where function g equals k, where f reaches maximum value. And so that's kind of marked with a bigger point. So what is special about that point that's not true at other points? So if you consider any other point along the constraint, you'll notice that the constraint curve is intersecting contour lines for f. This is no longer true at the point where f has been optimized. Right there, the constraint curve for g and the level curve for f are just tangent to each other. Now, of course, we've been calling it the constraint curve, but notice that constraint curve in math, g is the function g is just some constant. It's just a level curve. So what we really want is for at the place where f reaches its highest value, the level curves of two functions must be parallel. So how can we actually make that how can we mathematize that into some kind of equation? Well, typically the way we talk about the direction of a line is by using a vector. Now, relative to a contour line, what's the easiest vector that we can create? By taking the gradient, we can make a vector that is perpendicular to the contour line. Therefore, if we take the gradient of g and the gradient of f, those two gradient vectors must also be parallel. And in order for two vectors to be parallel, one must be, as we know about vectors, one must be a multiple of the other. So our big defining equation for this technique is right here. The gradient of f equals some constant times the gradient of g. So that constant, that's a lambda, that's a lowercase l in Greek. So in particular, note that the gradient is a vector. So this is actually going to give us a couple of equations. There's going to be one equation for each component. So if we have a function of two variables, that's going to give us two components in the gradient, so there'll be two equations. If we have n variables, we'll have n equations. Now, we just introduced some new constant, and we don't know what it is, so that's actually like a new unknown variable. So altogether, we've got n plus 1 variables. However, the constraint, if you go back to g of x, y, or whatever equals k, that is another equation. So put it all together, we wind up with n plus 1 variables and n plus 1 equations. And that is something that we can solve, hopefully. Now, it's easiest to draw the picture of this discussion for functions of two variables, which is what we did with this contour map. Everything continues to be true for any number of variables. So one comment about the notation. So that constant is called the Lagrange multiplier. Now the reason, so most textbooks use this lambda, and the reason for that is that this technique is credited to the mathematician Lagrange. So when I'm typing the lambda is a little bit of a challenge, so I'll just sometimes use C for the constant. Okay, so that is the key equation for this technique. Let's look at a problem. Let's see how this works. So let's jump right in with an application. So let's minimize the surface area of a cylinder with a volume 100 cubic centimeters. So first we have to set this up. We actually have to create the functions that we are going to be using. F, the one we want to optimize, and G, the one for the constraint. So first of all, what is the formula for, so the question is to minimize the surface area, we need a formula for surface area. What's the formula for surface area for a cylinder? So surface area S for a cylinder is, there's the top disk and the bottom disk. So each of those gives us a pi r squared of area, so that's 2 pi r squared. And then there is the lateral area of a cylinder. And so the area for that is 2 pi r times h, the height of the cylinder. That's something that you should have seen before, but if not, you can look elsewhere to find the background for where that formula, to find more information about where that formula comes from. And then the constraint is the volume of the cylinder. So volume of the cylinder is pi r squared h, but we know that that equals 100. So V equals pi r squared h, and that equals 100. So notice that in this problem, the function we're trying to optimize, we're calling S, and the function giving us the constraint, we're calling V. So before I introduce how we solve this problem using the Lagrange multiplier technique, I just want to shout back for a second to the way that the technique that you could have used in single variable calculus in order to solve this. You may even have solved a problem very similar to this. So, old method, eliminate one variable, so we get a single variable function. So notice that using the constraint, we can solve for h, and now we can substitute that into the function s for surface area, and now you've got a function in just the variable r. Take the derivative, set it equal to 0, and then solving out for r, you get this, or I say r cubed gives you 50 over pi. Solving out for r, you get the cube root of 50 over pi, which is approximately 2.52. And since we're working in centimeters, those are the units. And it said to find the minimum surface area, so we're not done solving. We now need to find h. Well, we previously solved for h, and so we can use that to calculate that h is approximately 5.03 centimeters. And then plugging into the function for s, the minimal surface area is approximately 119.34 centimeters squared. Okay, now that was the old method, which should look a little familiar. But now we'll talk about how to do it using the new method, Lagrange multiplier. So we need to take the two functions and take their gradients, and their gradients must be parallel. So the gradient of our surface area function S, so I set it up so that partial r is on top and partial h is on the bottom. So derivative with respect to r for the function s is 4 pi r plus 2 pi h. Then the derivative with respect to h, you get 2 pi r. Next, for the v function, the derivative with respect to r, 2 pi r h. Derivative of v with respect to h is pi r squared. Okay, so now that we calculated the two gradients, they must be parallel, so the gradient of s equals a constant times the gradient of v. Notice that because there are two components, this is going to give us two equations. So let's write those things down. So in equation 1, we will get 4 pi r plus 2 pi h equals some constant times 2 pi r h. And then the second equation will give us that 2 pi r equals some constant times pi r squared. So before we go ahead, it's very easy to simplify, reduce each of these equations a little bit. In the first equation, you can divide through by 2 pi, and in the second equation, you can divide through by pi. So now we've got these two equations, and also remember that we've got the constraint equation, which is pi r squared h equals 100. So notice that now we've got three equations and three variables. So now we confront the issue of we need to solve these. Now this is quite a bit easier to solve three variables and three equations when you have linear equations. In these problems, typically you will, or almost always you will not have linear equations. So how can we solve it? So we're going to need to eliminate variables one by solving for each variable one by one. Now, which variable should we start with? It's usually easiest to start by picking one equation and solving for c and first eliminating c. So the easiest way to do that is if we go to equation 2. Using equation 2, we get that c equals 2 over r. And so now we can substitute for c anywhere that we have c. And so in the first equation, so we can plug that into the first equation. So next we'll want to eliminate h. So one way to do that is to solve in the constraint equation. So solving in the constraint equation, we'll get h equals 100 over pi r to the negative 2. And now anywhere that we see h, we can eliminate h. So plugging both of those back into equation 1, we have 2r, take a moment to digest that. So plugging all of those into equation 1 will give us one second. Try to get a look at everything all at once here. Sorry. Okay. There you go. Okay. So plugging into this equation, we've got an expression for c and an expression for h. So that gives 2r plus 100 over pi r to the negative 2 equals 2 over r times 100 over pi r to the negative 2. And notice that we've eliminated c, we've eliminated h, and now we've got just an equation in r, and now we have to go ahead and solve that. So shuffling stuff around, we get that r cubed equals 50 over pi, then you just take the cube root, and r equals the cube root of 50 over pi, which is approximately 2.52. And from that, we take the equation for h, and we get that h is about 5.03 centimeters. And finally, we figure out what the surface area S was using the original formula for the surface area. This was the formula for the surface area, plugging in for r and h, and you get approximately 119, and that's square centimeters. Okay. So we have this old method that you've seen previously, and this new method, Lagrange multipliers. Okay, with two variables, both methods may work with about the same level of difficulty. That's about what happened in this problem. What if you have three variables? Let's take a look. So let's try to answer this question. A rectangular box without a lid will be made from 12 square meters of cardboard. Let's find the maximum volume. So notice that what we're trying to maximize is the volume. We'll need a formula for the volume, and the constraint has to do with 12 square meters. That's the surface area. So we'll need a formula for the surface area. So first, the volume V is XYZ. You could also use length, width, height. You could also use LWH. I chose XYZ. Now, what about the surface area? Notice that this rectangular box does not have a lid, so there are only 5 sides. So 2 of the sides will have area XZ, 2 of the sides will have area YZ, but then there's one there's the missing lid, so then the bottom will have the surface area of XY. So there's the formula for the surface area, and that must equal 12. So there's the setup. Now, we need to choose a method to do the calculation. What if you try to do it by the old method? Eliminate one variable and then set derivatives equal to 0. Well, first of all, notice that we're starting with 3 variables. So even if we eliminate one variable, we will still have 2 variables. Well, okay, what does that look like? Using the constraint equation to solve for z, we get this expression for z, 12 minus xy over 2x plus 2y. So now, plug that into the function v. And you get v equals xy times all that business. Written out, you get this, 12xy minus x squared y squared over 2x plus 2y. Well, now you've got to set all derivatives equal to 0. Well, derivative of v with respect to x is that, and that must be 0. Derivative of v with respect to y is that, and that must equal to 0. So now you've got those two equations in x and y, and you have to solve them. Let's stop right there, because solving those two equations in 2 variables will be an algebraic mess. That looks hard. We don't want to do it. Fortunately, we don't have to. Instead, let's use the Lagrange multiplier method. So we go back to our the 2 functions that we want to work with. Function v for volume, the function s for surface area. And we know that their gradients must be parallel. Therefore, we calculate their gradients. So the gradient of v, so dv dx is yz, dv dy is xz, and dv dz is xy. Next, the surface area function. ds dx is 2z plus y, ds dy is 2z plus x, and ds dz is 2x plus 2y. Those are the 2 gradients, and they must be parallel. Therefore, the gradient of v equals some constant times the gradient of s. Notice that we have 3 variables. That gives us 3 components in the gradient, and that will give us 3 equations. Let's write those equations down. Equation 1, yz equals c times 2z plus y. Equation 2, xz equals c times 2z plus x. And then equation 3, xy equals c times 2x plus 2y. And then remember that also we have the constraint equation, which was 2xz plus 2yz plus xy equals 12. So now we've got 4 equations in 4 variables, and we have to solve that. So again, it's important to organize this solving method. It's not as straightforward as linear equations. And typically the first thing you want to do is use one of the equations to solve for c and eliminate c. So there's a couple different ways to go. I'm going to choose equation 1 to solve for c. So do that and you get c equals yz over 2z plus y. And now we can eliminate c by substituting. So in equation 2, plug that in and you get xz equals yz times 2z plus x over 2z plus y. So let's simplify that equation a little bit. Cross multiply, multiply out, and simplify some more, and you wind up with the very nice x equals 2z. Next, we eliminate c from equation 3. Plug that in. You get xy equals yz times 2x plus 2y over 2z plus y. Solve that. Cross multiply, multiply out, cancel and simplify, and you wind up with the very simple x equals y. So now we can replace things. So we could get rid of any 2 variables. We could now replace y if we like, or replace x, or replace z, however we like. I'm going to choose to eliminate x and y, be left with z, just because that's going to leave me with no fractions. You could also eliminate z, y, end up with x if you like. Either way. So replacing replacing x's with 2 z's and replacing y's with 2 z's, and plugging that into the constraint equation, that gives you 4z squared plus 4z squared plus 4z squared equals 12. 12z squared equals 12, z squared equals 1, so z equals plus or minus 1. Now remember that in the original problem we're trying to find lengths on these sides, so we're going to take the positive value. So z equals positive 1, and then from that we know that x equals 2 and y equals 2. Plugging it back into the equations that we had before. So finally we know the dimensions must be z equals 1, x equals 2, y equals 2, and therefore the maximum volume is v equals xyz equals 221, and that's 4 cubic meters. Let's take a look at another problem. One small comment before we do. We can confirm this is a maximum by taking the other boundary critical point. So remember that z was -1. That would give us a critical point -2, -2, -1. Plugging that in would give you v of that would give you -4, and that's going to be a minimum value. Now, of course, that's the minimum value for the function. That can't actually happen because you can't actually get a negative volume. But there's your maximum volume. Okay. So that is that application. Let's look at another example of how to use Lagrange multipliers to do this optimization. So let's minimize the distance between the point -3, 0 and a point on the parabola y equals x squared. Okay. So first, as always, we need to create the functions that we are trying to optimize. So the function we're trying to optimize is the distance function. So the distance between these two things, we just use the distance formula. So the point xy and the point -3, 0, the distance is going to be the square root of x minus -3. So x plus 3 squared plus y squared. Now, we know in the future we're going to have to take derivatives. When you have a square root in a function, that makes taking derivatives a little bit of an algebraic annoyance. So we're going to use a little bit of a trick here. And the trick is that, the helpful trick, is minimizing the distance is exactly the same, or occurs at the same spot where you minimize the distance squared. And also the math clearly will be easier. Therefore, we're going to minimize the function distance squared, which is f of xy equals x plus 3 squared plus y squared. So that's going to happen at the same point, and then just to find the distance, we will plug it into the original distance function at the end. So what's the constraint? So we have the function we want to minimize. The constraint is y equals x squared. Now this does not look like a level curve equation. We've got to turn it into one. So we move everything to one side. So we get y minus x squared equals 0. So g of xy equals y minus x squared equals 0. That's my function, and now it's written as a level curve of a function. And now that we've got the function we're trying to optimize f, and then the constraint g equals 0, or as a level curve, now we know that their gradients must be parallel. Therefore, the gradient of f equals some constant times the gradient of g. And now we can do our calculations. So by taking the gradients, the partial derivatives, and using the Lagrange multiplier, our first equation is going to be df dx, which is 2x plus 6, equals a constant times dg dx, so that's c times -2x. Then equation 2, with the partial with respect to y, we get that 2y equals c times 1. And of course, we also have our constraint equation, y equals x squared. So 3 equations, 3 unknowns. Let's go ahead and solve. So right off the bat, the typical first step we like is to solve for c. It just so happens that equation 2 has already solved c for us. That was very thoughtful. So we can now get rid of c. So in the first equation, substitute, and you get 2x plus 6 equals 2y times -2x. And further, the constraint has already solved for y, so we can replace y. So this gives us 2x plus 6 equals 2 times x squared times -2x. So working that out, we get 4x cubed plus 2x plus 6. So some clever guessing, or if you like the rational roots theorem, we quickly find the solution, or we know that x equals -1 will be a solution, and using that, and then using perhaps synthetic division to factor it out, we get that this factors out as 2 times x plus 1 times 2x squared minus 2x plus 3. And using the quadratic formula quickly tells you that that quadratic does not factor with real numbers, so the only real solution is x equals -1. Plugging in, we get that y equals -1 squared, so y equals 1. So this tells us that our only critical point is -1, 1, and therefore the minimum distance is going to be, plugging into the distance formula, -1 plus 3 squared plus 1 squared. Square root of all that gives us the square root of 5. And note from the original problem that we found this is a critical point. The maximum distance is clearly infinity, because we're talking about the distance between some point and somewhere on a parabola. So the maximum distance could be infinity. So then logic tells us that this critical point, yes, is in fact a minimum as we designed. So that was a look at 3 different examples of how to use the Lagrange multiplier technique in order to optimize, meaning find a max or min, when we're for a function when we are given a constraint equation.